All right, so we're looking today at chapter 14. Chapter 14 is another organic chemistry chapter. So last week we were looking at carbohydrates. That was our first biochem chapter. Now we're getting back to organic here. Now I will warn you, everything that is in chapter 14 is not everything that we're going to be covering. There are going to be parts that we are going to skip and kind of gloss over and not even touch in some cases. So if you're looking at the reading assignments, I don't know how many of you have been doing the reading assignments, but if you've been looking at them, take a special note of, I put in the description for the 2 assignments, there are some things that you don't have to read out of some of those sections. So for example, when we talk about esters, you don't need to read the section about how to name an ester. We're not going to cover that. On Thursday, when we talk about amides, you're not going to have to read the section that talks about how to name amides. We're not going to do that. Any naming that we talk about is going to be of the variety where we are basically taking what we already know how to name and then just changing the ending because it's an acid instead of alkane. So let's talk today. We're going to look at carboxylic acids and esters. And so what we see in carboxylic acids, we talked about this a little bit in chapter 11. We talked about this a little bit in chapter 12, rather. Looking at alcohol groups and how alcohol groups can react and turn into aldehydes and turn into acids through these oxidation processes. Well, what is an acid? Well, an acid is a combination of 2 things. We've got the carbonyl group, the C double bonded to the O, and we've got the hydroxyl group, the OH, and they're all on the same carbon. So carboxylic acids in a lot of ways have some things in common with aldehydes. So if you remember an aldehyde, you had the carbonyl group on the end and a hydrogen hanging off of it. Well, in an acid, you've got a carbonyl group on the end, but an OH hanging off of it instead of just an H. Another way of thinking about acids, acids are kind of the bringing together of a carbonyl group and an alcohol group. So I've got the CO and I've got the OH. And because of what it is positionally, it can only exist at the end of a chain. Because I've got carbon that's double bonded to oxygen and has a single bond to another oxygen. So there's 3 of the 4 bonds that carbon can make. It only has room to make 1 more bond to carbon. So carboxylic acid groups, like aldehydes, have to exist at the end of a chain. And when it comes to their naming, just like we saw with aldehydes, we're going to always number from that acid group. So the carboxylic acid group will always be the 1 carbon. And then we can number out from there. Like we saw with aldehydes, there are 2 different naming systems that can be used. Luckily for us, the common, less formal naming system is exactly the same for acids as it was for the aldehydes. So you know how we had formaldehyde and acetic aldehyde, propionic aldehyde? Well, it's the same ideas. Formic acid, acetic acid, propionic acid, butyric acid. Those same four prefixes, form, acid, propion, butyr, are used in both. It's just the ending that changes. Instead of aldehydes, we call them acids. Now, as far as the IUPAC is concerned, all that we do for the IUPAC system is we change that E at the end of the alkane to oic acid. So a 1 carbon methane would become methanoic acid. A 2 carbon ethane would become ethanoic acid. 3 carbon propane, propanoic acid. Aside from this suffix change, everything else we know about naming from the previous 2 organic chapters applies here in terms of how do we number, what order do we put the side groups, all of that. All of that comes out the same kind of way. So if I have a chain such as this, where I've got a 4 carbon chain, 1, 2, 3, 4. Well, I know that the 4 carbon acid would be butanoic acid. It would just be a matter of naming that methyl group. And since it's on the 3rd carbon, it'd be 3-methyl butanoic acid. One other important note, if I have a benzene ring, with an acid group attached, the formal name for this compound is benzoic acid. And so if there are side groups, all we have to do is we number the side groups starting with the acid group as number 1 on the ring and numbering around to whatever combination gets us the lowest set of numbers. And so that's how we come up with 2,3-dichlorobenzoic acid here. Benzoic acid is kind of the base model because we've got the benzene ring with the acid group on it. The numbering of the chloro groups just comes from starting at that acid carbon where the acid is attached to the ring. That's number 1, and then numbering from there, always giving us the lowest combination of numbers possible. So like I said, kind of in the intro here, one of the benefits that we'll have between exam 2 and exam 3 is another month of just kind of reinforcement of all of those organic rules. And so hopefully over this next month, because we'll have another 3 weeks of exposure, we'll be that much better at organic naming just by mere practice from seeing it over and over and over.
So we have 4 total exams, the 5th one the final.
Correct. Now, like I said, the first 4 acids do have common names as well, just the same as the first 4 aldehydes had common names. And for those, we just take that prefix, form, acid, propion, butyr, and we add ic acid to the end. So 1 carbon is formic acid, 2 carbons is acetic acid, 3 carbons is propionic acid, 4 carbons is butyric acid. And yes, I do recognize that the IUPAC name and the common name for the 3 carbon acid are really similar, but yet different. Propanoic versus propionic. Can't do anything about that. Okay, go ahead. Yes, it's the combination of the 2 together. So without the OH, we'd be talking about a ketone or an aldehyde. Without the carbonyl, we'd be talking about the alcohol. The 2 of them together, that's what makes it an acid. A couple of your more common carboxylic acids, methanoic acid or formic acid. This is the substance that in red ants in particular, when they sting you, that stinging sensation is formic acid. So inside of the saliva or whatever it is that they put on you when they bite you, that is the substance. Another really common one, acetic acid, known less commonly as ethanoic acid, but what we're talking about here is a 2 carbon acid. This is the active ingredient in vinegars. So vinegar, commercial vinegar is usually a 5% solution. So 95 parts water, 5 parts acetic acid. The different kinds of vinegar largely come from the source material. So vinegar is a byproduct of the overoxidation of sugar. So you oxidize sugar, it turns into alcohol. And most of the time, that's exactly what we want it to do. You turn grape juice, you let it ferment, it oxidizes, it turns into alcohol, we call it wine. You let that sit around too long, and it continues to oxidize, it continues to ferment, your wine turns into vinegar. Now, if you do this intentionally, that's how you can get different kinds of vinegar. Red wine vinegar is derived from, you guessed it, red wine. Take the red wine byproducts, you add a bunch of water to it, there's your red wine vinegar. Malt vinegar, same kind of idea. Again, you're taking it's the source that gives it its unique tendencies and unique flavors. But at its heart, it's acetic acid. It's acetic acid mixed with water. So the acidity level really, I don't know if it could go sour versus spicy there, but it would go, the acidity level is basically, that's what gives the vinegar its punch. Now, if you're having different kinds of things, other flavors other than sourness probably have more to do with the source material and perhaps what else is present in it. So if I take vinegar and introduce it to a bunch of hot peppers, the vinegar is going to extract some of the capsinoids out of those peppers. It's going to make the vinegar taste hot. So it's not really the vinegar that's hot. It's the fact that we mixed it up with the hot peppers and the vinegar was able to extract those flavors. In that sense, yes. In that sense, yes, because the more vinegar you're adding, the more extraction power you're going to get, because the acid is going to break down those chemical barriers that are trapping those capsinoids to make the salsa spicy. Okay. Let's go and do a couple of naming examples just to get into the habit. So again, the combination of the carbonyl group with this hydroxyl group, we collectively refer to this as a carboxylic acid functional group. So in both of the homework sets for this chapter, I've put in some specific questions asking you to identify functional groups. When I'm asking you to do that, this is the kind of thing I'm looking for you to do. Identify specific clusters of atoms or specific characteristics that would help you to identify, okay, this is an alkane, this is an alkene, this is an alkyne, this is an alcohol, this is an acid, this is an aldehyde. Each one of those things has specific markers on it. Things that you would look for that would say, oh, this is a ketone. I know it's a ketone because I've got a carbonyl group and it's got nothing else. It's in the middle of a carbon chain. So here's our acid. Now we've got to name this off here. So we're going to number our chain. This carbon right here is going to be carbon number 1. And we know it's carbon 1 because we always number from the tail that has the acid group on it. So there's 1, 2, 3, 4, 5. 5 carbons in total. So I know I'm dealing with a pentanoic acid, because I can combine the two things I know already. 5 carbon chain, so that's pentane. Carboxylic acid means I change pentane to pentanoic acid. All I'm doing is changing that ending from E to oic acid. Don't need to put a 1 on there because acids are always at the end of the chain. All that's left is this guy. This is off of the chain. It's a methyl group, and it's in the 2 position. So we would call that side group 2-methyl. Now I just need to put the 2 together. 2-methyl pentanoic acid. No. So the last terms are always shrunk together. So there is a space between pentanoic and acid, but there is not one between methyl and pentanoic. It's always the case. The last terms of the name are always put together, unless you have to signify it by a number. So like, if you've got a ketone, then you have to put, 2 hexanone. And that would be the last bit of it, because you've identified all the side groups, and now you're identifying the specific location of the ketone. But in this case, we only have the 1 side group, so we don't need to put the space in between. All right, questions with this example? Okay, try these 2 on your own then. I've got 2 different acids here in play. Give me the name of each of them. So take a couple of minutes, go ahead and do that. And then we'll check and see how everybody's doing in a second. All right, let's see how we did. So in the first one, obviously we had to recognize the acid group, which since we were told they were acids, we kind of knew that was coming anyway. But we also had to recognize this was a 3-carbon acid, so propanoic acid would have been the base. And then it would just been a matter of identifying the methyl group in that second position. So 2-methyl propanoic acid would have been the correct IUPAC name. Now, if you were asked for a common name, 2-methyl propionic acid would have been acceptable there. The common name system is pretty much exactly the same other than just how we named the base. For the second one, we had to recognize that we had benzoic acid, so that was our base, not just the acid group, but the fact that the acid group was on that benzene ring. And from there, it was just a matter of counting down from that carbon position, the acid, to the bromo group, which put us at 3-bromo. So 3-bromobenzoic acid was the correct answer. All right, any questions with either of those two examples? So like I said, acid naming isn't terribly difficult if we understand how to fix the end of it. Because after that, it's exactly the same as what we've done for every other thing in terms of how we deal with side groups and how we number it and all of that other stuff. It's just a matter of practice. And we're going to get better at the practice because we're going to keep doing this kind of stuff over and over. All right, let's go the other direction. Draw the skeletal structure for 4-chlorohexanoic acid. Again, I'll give you another minute or so to do this. All right, so in this one, same kind of idea. We're just kind of going in reverse here. So we kind of want to reverse engineer this, if you want to think about it that way. So if we start with hexanoic acid, we understand that hex means 6. So I have a 6-carbon acid here. So I'm going to start drawing 2, 3, 4, 5, 6. Now it's an acid, so it needs to have the acid group at the end. And again, personal preference here. I like to draw my acids and aldehydes with the last group on the right, just so that I don't have to try to draw backwards. But I can still see that from a counting standpoint, I've still got 6 carbons here. So I've covered the hexanoic acid part. Now I need the 4-chloro part. So I've identified the 4-carbon. And so a chlorine group is going to be hanging off of that 4th carbon. There's my 4-chlorohexanoic acid. That's all I have to do. So again, it kind of comes down to, if you understand what the name is trying to tell you, just start working it backwards. Start at the very front. What is hexanoic acid? What does that look like? Okay, I've got a 6-carbon acid. So here are my 6 carbons. Here's my acid group. And now I can start to handle any of the stuff in front. All right, questions with this one? So like with you, what you had to do in chapters 11 and 12, you're going to have to do here. You're going to have to be able to go forwards and backwards. Structure to name, name to structure. Okay, section 2 here. Now, in section 2, we are actually going to skip a good chunk of this. In fact, we're going to skip almost all of it. There's just a couple of things that we want to mention. Now, why are we skipping a big chunk of it? We haven't talked about acids and bases yet. And in terms of the reactions that acids and bases do, we're going to come back to that a little later on in the semester. And when we do, we'll circle back to this conversation about talking about carboxylic acids specifically. What we're going to focus on mostly here is solubility. And solubility of carboxylic acids comes down to this idea of polarity. All solubility comes down to polarity. What we need to understand is that the polarity of carboxylic acids is stronger than the other kinds of stuff that we've looked at thus far. Carboxylic acids are the most polar of the things that we have talked about to this point in time. And the primary reason for that is you've got a carbonyl group, which we saw in ketones. That carbonyl group makes the ketone polar, allows small ketones to dissolve in water, but large ketones have a hard time doing it. And we've got that hydroxyl group, which allows alcohols to dissolve really well in water. But again, we were always limited to small alcohols dissolve, big alcohols don't really. Well, now I've got the combination. I've got a carbonyl, which is polar, and a hydroxyl, which is also polar. The end result is I've got a really polar molecule, capable of forming hydrogen bonds, which we know hydrogen bonding is the strongest of the intermolecular forces for a covalent compound. So really strong polarity in carboxylic acids. And what that means is that we get an increase in polarity. Carboxylic acids up to a chain length of 5 are pretty good in terms of their water solubility. And so if we contrast that with alcohols and with ketones, aldehydes, we see that this is a little bit better than any of those were. We also noted that with each of those, solubility kind of dropped off a cliff pretty quickly once we got to a certain chain length. And what we see is a similar kind of effect, but not nearly as drastic. So carbons 1 through 5, so methanoic acid all the way to pentanoic acid, we get pretty good water solubility. From there, it starts to level off, and then eventually that chain length just becomes so much that even having that really polar group on the end can't overcome the non-polar hydrocarbon. So what we see, again, first 5 carbon chains, all those acids are soluble. We get to number 6, hexanoic acid. We see that there is still solubility there, but it is reduced. We change that from a chain of 6 carbons to a ring of 6 carbons. Same kind of idea, slight solubility. Go from 6 to 7, it's reduced even further. Go from 7 to 8, it's reduced even further. By the time we get to 8, it's starting to kind of border into that. It doesn't really dissolve all that well at all kind of territory. And that's it. That's all that we're talking about out of that particular section. Now you'll see if you go to read the chapter, that there is a lot of information in there about chemical reactions that acids can participate in. We're not going to cover those here. Again, we'll circle back to it when we talk about acids and bases a little bit more formally, but we're not gonna do that at this point in time. And so we're going to move on to the last topic for today, which is the ester. Now, esters are an interesting kind of compound. And what we see a lot with esters is we get a lot of application in esters. So the primary example that we get off of this, what they're introducing us to initially here, is the idea of the discovery of aspirin. And so turning aspirin, turning salicylic acid into acetyl salicylic acid, which turned an acid into an ester, provided some of the same relief, but without the stomach irritation in terms of what it did to your body. So what is an ester? An ester is the product of the reaction between an acid and an alcohol. So if we look at what acids and esters have in common, we can see that the common thread between an acid and an ester is that an ester retains everything other than the H of the acid. Now, where does that H go? Well, that H ends up being a byproduct of the reaction. So to make this compound, we had to start with this compound, CH3OH. So here is our alcohol. Here is our acid. We can see that the alkyl portion, the hydrocarbon portion attached to this oxygen. So what's left? You've got the hydrogen from the H and the hydroxyl from the alcohol, HOH. These esterification reactions always drop behind water molecules as they react. So when we bring that acid and that alcohol together and they make an ester, they also make a water molecule. Now, where we get a lot of our use out of esters, esters can be found in fats and oils, but where we really see them a lot is in flavorants. Flavorants and fragrances. Esters are responsible for what makes a strawberry smell like a strawberry, and in a lot of ways taste like a strawberry. They are what are responsible for the flavor and the aroma of bananas, oranges, and a whole bunch of other fruit flavors. And if you look closely at the labels, probably won't find a whole lot of esters there. What you'll see instead are natural or artificial flavors. But esters are responsible for a lot of them. And we'll get into some of the more common examples here in a minute, especially when it comes to fruit flavors. So here is an esterification reaction. So they drew it up a little bit differently than I did on the previous. Here we've got our carboxylic acid. Here we've got our alcohol. And what we can see is that the OH from the acid gets ripped off and combines with the H of the alcohol. That's what makes the water. So we still get water. HOH is water. Now, these kinds of reactions happen in two specific environments. First of all, we need heat. If I just put an alcohol and an acid together, they're not going to react and give us an ester. I've got to heat it. Usually that means I got to heat it a lot. The other thing that I need, this H plus here, this is acid. So usually the acid that gets used in these kinds of cases is something like sulfuric acid, where the sulfuric acid can't accidentally insert itself into the reaction, whereas a hydrochloric acid could, because that chloride group could end up inserting itself into this, making a mess of everything. So acid and heat will allow these two things to come together and make the ester. In the absence of either the acid or the heat, it becomes a lot more difficult. Minus the heat, the reaction won't run. Minus the acid, the reaction will run, but it'll go really slow. You need both. So here's another example of an esterification reaction. Here we've got ethanoic acid, acetic acid, reacting with 1-propanol. And the resulting compound is something called propylethanoate. Now, don't worry. You don't need to know how we came up with that name. I'm not going to ask you any questions about the naming of esters. You can probably figure out how it came about. You've got a propyl group on the one side of the ester. You've got the ethanoic acid on the other side. That's kind of how it goes about in terms of naming. But again, not going to hold you responsible for that. Now, propyl acetate or propylethanoate, depending upon which source you're looking at, this is actually the primary smell that we associate with pears. Now, pears on their own don't have a really strong, potent odor. But if you get close enough to a ripe one, you can tell there are certain things that would distinguish it from, say, an apple or an orange or a banana. All right, let's do this one together. Write the balanced chemical equation for the reaction of propionic acid and methanol in the presence of heat and acid. So to do this, we need to have all of these formulas all written out. So propanoic acid, I've got a 3-carbon acid. So 1, 2, 3. There's my propanoic acid, methanol. Oops, that's too much. in the presence of heat and acid. Now for heat, sometimes you will see one of these triangle looking things instead of heat. It's actually the Greek letter delta, but that is a universally accepted symbol for heat. So sometimes you'll see that instead of the word heat, just so you know. So in the presence of heat and acid, we're going to get two things. We're going to get water. Coming from the OH and the H that were reacted. And the other thing that we're going to get this CH3O is going to go on to this carbonyl carbon. Now, honestly, even though it's not technically correct, there's a reason I drew it out this way as opposed to the other way when trying to figure out what goes where. I've always found it easier to think about this ester group as staying together and then just attaching whatever was attached to that OH instead of this popping off and this O whatever group popping on. The end result ends up being the same. It's just that technically speaking, if we're looking at it from a reaction standpoint, that's not how it happens. So if that helps you, go ahead and just think about it that way. And so again, what I'm talking about there is if it's easier for you to think about this reaction as this H and this OH are what make the H2O, so that you can see that all that happens is that this CH3 group comes onto this oxygen. That's easier for you visually, just go with it. Now, like I said, in reality, that's not how it happens. The acid actually is the one that loses the OH, not the alcohol. But again, from a visualization standpoint, if all we're interested in is getting the correct formula and structure for the ester, the mechanics of how we got there isn't nearly as important. Now, if you're a second-year organic student, yeah, obviously how we got there makes a big difference. But for us, it's not that big of a deal. All right. All right, any questions with this example problem? All right, similarly to section 2, everything in here about naming esters, don't worry about it. What we want to look at as far as the rest of this section is concerned is we want to start looking at applications because that's really the interesting stuff. So salicylic acid. Now, when we opened up this particular section, we talked a little bit about salicylic acid. Salicylic acid is derived from the bark of a willow tree. And the problem always with salicylic acid was that even though it was good at reducing inflammation and relieving pain, it irritates the heck out of your stomach when you ingest it. So in 1899, the Bayer Chemical Company takes salicylic acid, which is this one here, and creates an ester out of it. So reacting this acid with this one, we created what is called acetyl salicylic acid. Acetyl salicylic acid, you know better as aspirin. And so Bayer aspirin, inventors of aspirin, this is their product. Now, how it works is it's basically an anti-inflammatory. It works at reducing inflammation inside your body systems. Why it's used for heart attacks in particular, for blood vessels, is reducing the inflammation of your blood vessels can basically cause them to dilate a little bit more, allow blood flow to go through them a little bit easier. And so low-dose aspirin, or baby aspirin, as it's sometimes called, this is the kind of aspirin that people that are heart patients can end up taking just to, as a preventative measure, help them to reduce the risk of heart attack, reduce the risk of stroke, because both of those conditions are largely related to blockages. And if you reduce the inflammation of your blood vessels, cause the openings to be a little bit larger, the chances of having a blockage go down. Another derivative of salicylic acid is oil of wintergreen. Oil of wintergreen, methyl salicylate, comes from the reaction of salicylic acid with methyl alcohol, methanol, and we get methyl salicylate. I know. Yeah, you gotta stand in front of a mirror and practice acetyl salicylic acid about 200 times. Now, oil of wintergreen, probably are familiar with, at least in some kind of way. It's used in skin ointments. So these are your icy hots, your Bengays, some of those pain medicines. They have a very specific odor to them that you know and recognize, and that is the oil of wintergreen. Huh? Mm-hmm. All right, another common application of esters, or at least another common place where we find them, is in fruits. Lots of fragrances, perfumes, flowers, fruits come from these ester compounds that naturally exist inside of the plants. And so what makes them interesting, what makes them noticeable to us is, for the most part, these compounds are small. Since they are small, they have relatively small intermolecular forces, which means they become gases really easily. And since they become gases really easily, that's going to allow us to smell them. They also happen to be soluble in water, which allows us to taste them, because they can interact directly with the taste receptors on our tongue. Now, the ones that we see, the most common examples we have are those that are associated with pears, bananas, oranges, pineapples, and apricots. So pear, we already talked about, that's a propyl acetate. In bananas, that specific ripe banana smell that you know is pentyl acetate, so pentyl ethanoate. In oranges, that citrusy smell that we associate with a lot of citrus fruits, but specifically with oranges, that's octyl ethanoate or octyl acetate. Now, not to be confused with citric acid and ascorbic acid, which are the key factors behind the flavors that go into those particular fruits. That sourness that we get, that's your citric acid, that's your ascorbic acid, the vitamin C. That's what those are doing. But the smell of orange rind, that oil that comes off of orange peels, that's this ester. For pineapples and apricots, we're dealing with butyrates instead of acetates. So we're dealing with a longer acid chain. And so in pineapples, it's ethyl butyrate. In apricots, it's pentyl butyrate. But these substances are the basis of fragrance. They are the basis of natural flavorant. And if we derive them, they can become what we would call artificial flavorants. So on food labels, they don't have to usually be disclosed. They kind of come under that heading that you see on some labels, natural flavors, artificial flavors, usually they're esters. Okay, so that is the end of this first section that we're going to talk about and what the subject of the homework that is due Thursday night is all about. I've got about 5 minutes. This section on amines and amides is a little bit longer. So I'm just going to take a couple of those minutes just to kind of introduce amines and amides. They do have a lot of commonalities between them, which is why they're being presented together. But just kind of keep that in mind. So for amines, what we're going to be looking for in amines is the presence of nitrogen. Amines and amides are nitrogen containing organic compounds. So we still got the hydrocarbon, we still got the kind of the structure, but now we're introducing a nitrogen into the mix. So the reason they are called amines is because they are derivatives of ammonia. Ammonia is NH3. What we have in an amine is a hydrocarbon derivative of that ammonia. So what we're doing is we're taking one or more of those hydrogen groups off of ammonia and we're replacing it with some kind of a hydrocarbon. And that hydrocarbon group can be just a simple methyl group, ethyl group, propyl group. It can also be aromatic things like benzene. Now, in cases like this, when we've got a benzene ring with a amine attached to it. This has a slightly different name. We call that aniline. So kind of similar to what we saw with benzoic acid or benzaldehyde or phenol, where we had a benzene ring with an OH on it. When we introduce benzene rings into these other functional groups, sometimes we have a completely different name for all of them. So in the case of the amines, that benzene derivative is called aniline. And so if there were other things on that, we would just call them as such. We would start with aniline as our base, and then we could move on from there. And so, like I said, I wasn't going to go too deep or far here. I just kind of wanted to get the ball rolling a little bit, because there is more on Thursday, and I want to make sure that we don't run out of time on Thursday. So that's where I am going to stop. Just have kind of introduced the idea of an amine, of this kind of different class. And then what we'll see on Thursday is we'll talk a lot about amines, and then we'll talk a little bit about amides. And all that's different is that an amide is kind of like the ester for amines. Carbonyl group, nitrogen group, same carbon. So we'll get into that on Thursday. Good luck on your midterm. I'll see you Thursday.